here we go again. So it's my pleasure to introduce Omid Amini from École Polytechnique, who will speak about the Hodge theory of tropical varieties.
Thank you very much for giving me the opportunity to talk at this very nice event. So my talk is about tropical geometry. So I think it's a good occasion, probably in a tropical country, to talk about this. And also a beautiful landscape here. So the talk is about the interactions between Hodge theory and tropical geometry. And also it is maybe an introduction to aspects of tropical geometry, because tropical geometry is now a wide field. It has gone from, it started from very basic constructions, and now it has gone to many different branches of mathematics. So it's not going, my talk is not going to be an exhaustive introduction to tropical geometry. I am interested essentially in parts of the tropical geometry related to Hodge theory. Okay. So yeah, I will start by, please stop me if there is anything unclear. So it is supposed to be a panoramic talk. There are a lot of, a collection of results. If there is something unclear, please stop me. I will be happy to expand on it. Okay, so let me start by recalling, giving an overview of Hodge theory, of classical Hodge theory of complex, smooth, projective complex manifolds. So if you take, it's about the properties of the cohomology groups of smooth projective manifolds over complex numbers. So since this is a smooth manifold, you can, since this is a manifest topological space, we can associate to this topological space cohomology groups, homology and cohomology groups. And these cohomology groups verify a list of very nice properties. First of all, because X is smooth, you have Poincare duality. So this Poincare duality is given between the kth cohomology group of X and so the real dimension is 2D. So the Poincare duality is between kth cohomology group and 2D minus kth cohomology group of X with values in, so the cup product gives you an element of H2D, and if you take the integrate the form over X, you get a number. And Poincare duality tells you that this is a perfect pairing. But then, because X is projective, it is embedded inside the projective space. If you take a hyperplane inside the projective space and intersect it, sorry, it was a spoiler for what comes next. It was not, wow, what is this? Okay, I think I have some problems with it. Okay. I think if I press twice, it jumps to the, okay, sorry. Yeah, so if you start with the hyperplane section, the hyperplane inside the projective space in which X embeds, you take the intersection of that hyperplane with X, it gives you a hypersurface in X. And to that hypersurface, you can associate an element of H2 of X. And one of the central theorems about the cohomology of complex manifolds, projective complex manifolds, is that if you take, you know that the dimension of HK and H2D minus K are the same, but actually if you take, there's a map from HK to H2D minus K, which consists by taking the cup product with the right power of this hyperplane, the class of this hyperplane section. This is an isomorphism. Lefschetz, this was proved by Lefschetz. You get Hodge decomposition. So if you look at not working with Q coefficients, if you work with the C coefficients, then the kth cohomology of X decompose further into a direct sum of bigraded vector spaces. So since this is HK of X with C coefficients is the tensor product of HK X with Q coefficients with C, you have a complex conjugation which acts here. And this complex conjugation induces a symmetry between PQ part of this decomposition and QP parts of this decomposition. So this is called Hodge symmetry. And you have, so Hodge proved the generalized result of Riemann. He proved also that you have, you can you get a bilinear pairing on each piece of this decomposition, HPQ. So what you do is that you take two elements alpha beta. These alpha betas are PQ forms. So I mean, you have to do some analytic geometry. So you take the wedge product of alpha and the complex conjugate of beta, and then you take the cup product with the element, the right power of L. So this gives you, then you can integrate. And if you normalize it by the right power of a square root of -1, then the Hodge-Riemann bilinear relations tell you that it gives you the signature of this pairing. So you need to, I mean, the Lefschetz, by hard Lefschetz, the theorem, you get the composition of each cohomology group into primitive parts. Basically, Hodge-Riemann bilinear relation tells you that this is this pairing restricted to the primitive part is positive defined. So my goal is to give you an introduction to tropical geometry and tell you how you can get this type of statements about the cohomology of tropical varieties. So maybe you have seen, maybe just give you an idea of what is tropical geometry. Tropical geometry is about asymptotic complex geometry. It's about the geometry of complex varieties when they degenerate to singularity. So in this respect, it is connected to the lectures that we see this week about singularities. So it's really about the appearance of singularities in the limits of families of complex varieties. This is not the point of view that I will take. I will really introduce tropical varieties as you define complex manifolds or you define real differential manifolds. My approach today is to explain you how you can define tropical varieties by atlas of charts and how we can define the cohomologies, study the cohomologies, and so on. But everything I say is connected to to the three lectures actually. Okay, so let me start by telling you. So I will start with telling you how Hodge theory is related to combinatorics. So, and then I will tell you a little bit more about this will be an introduction, an opening to tropical world. So it's about combinatorial Hodge theory. What is combinatorial Hodge theory? Let me start with the classical result, which is in combinatorics related to the theory of polytopes. So you take, this is related somehow to toric geometry. So a smooth polytope, you take a smooth polytope, P, inside of dimension D. Suppose that this polytope lives in RD. So it's a full dimensional polytope inside. For example, if you are in dimension 2, what you have is this picture. I consider also the interior. So this is the polytope of dimension 2, but you can also have a polytope of dimension 3. Which is a cube. I consider also the interior of the cube. And one of the classical problems in the theory of polytopes was to characterize the F vectors. Maybe you have heard of the Euler formula for three-dimensional polytopes. You know that there are relations between the number of faces, of the number of vertices, the number of edges, the number of faces of a polytope. This is a generalization. So if I give myself a d-dimensional polytope, I can associate to this polytope a vector F0, F1, up to Ft. F0 is the number of faces of dimension 0, which means the number of vertices. So for example, in this case, in the cube, I have exactly 8 vertices. Then I have F1. F1 is the number of edges. So I have here 12 edges. F2 is the number of two-dimensional faces, and I can go up to Ft, which is the d-dimensional, the top dimensional face, which is the polytope itself. And Ft is equal to 1. Okay, so the question is how you can characterize all the F vectors of polytopes. This is a difficult problem, but it turns out that there is a classification of the F vectors of smooth polytopes. What is a smooth polytope? It is a polytope which looks like the cube. It has the property that if you look at every vertex, if you look at the vectors that you see here, okay, so these vectors, let's say we are in the rational case, there's generalization to any simple polytopes. But so if you take a vertex here, you look at these directions. So these directions are rational. So you have integer vectors associated with this direction, and they generate the full lattice of integer vectors inside RD. Okay, So if you take these 3 vectors, they are integer, you can make them integer, and together, any integer vector can be written as an integer linear combination of these vectors. This is the meaning of being smooth. Okay? So there is a beautiful classification of F vectors of a smooth polytopes. And this is the following theorem. So first of all, it's difficult to work, in order to get the classification, you have to transform your F vector to another vector, which is called H vector. So you do the following trick. You start by putting the coordinates of this F vector in the following form. You take Ft, you put it here, and then you put Ft minus 1, Ft minus 2, and you go up to F0, and you put the 0 here. And then you put a lot of 1s on the other side, 1 in each line here, up to here. And then you transform this into a sort of Pascal triangle, but instead of taking the sum, you take the difference. So every time you have 2 elements here, you put the difference of the value, this minus this. You put the difference. So let's see what happens if you start with a cube. So in the cube, I have F, so I have the first element of is F3, which is 1. I have 6 two-dimensional faces. I have 12 edges, and I have 8 vertices. And I put a 0 here. Then I put 1, 1, 1, 1. And now I transform this using the difference. So 6 minus 1 is 5. 5 minus 1 is 4. 12 minus 5 is 7. And I continue. 5 minus 1 is 3. 7 minus 4 is 3. 8 minus 1. 8 minus 7 is 1. Sorry. Thank you. Okay, so if now the vector I get here is called the H vector. You can put H, this is H3, H2, H1, and H0. So the last one, this is HD up to H0. This is called the H vector. Obviously, if you know the H vector, you can construct the F vector. Okay, so this is really classification of F vector and H vector are equivalent. And as you saw here, at the end, we get something which is symmetric. And it has a nice property that it is also unimodal. It starts with 1, and it goes up to the middle, and then it comes down to the middle. And it is actually a property of all the F vectors of smooth polytopes. So this is the characterization theorem. The characterization theorem was the conjecture of McMullen in the 70s. It was, and the sufficiency was proved by Bilher Ali 10 years later, and Stanley, he proved the necessity. Okay, so what is the characterization theorem? These are the necessary and sufficient conditions for an H vector to be an H vector of a smooth polytope. First of all, the HI should be non-negative. It should be symmetric, as here. And then it should be unimodal. It means that it starts it goes up to the middle, and then by symmetry, it should come down. But there is an extra condition, and the extra condition is that if you take the difference of HI, if you take the difference of HI minus 1, you get another vector, which is called the G vector. That's why this theorem is called G theorem, or G conjecture. And this sequence GI should be the dimension sequence of a finite dimensional graded Q algebra. Okay? A finite dimensional graded Q algebra. It means that GI is the homogeneous part of that algebra of degree I. Okay? And there is a classification, there's a combinatorial classification of the sequences. I don't have time to expand on this, but you can actually classify exactly what are the G sequences. Why I took this? Because it's a beautiful result, but also because it is related to Hodge theory. Let me tell you how Stanley proves. So the existence you have to prove that if you have a sequence like this, it's possible to construct to find a smooth polytope. the necessity of this, it's a consequence of Hodge theory, the results that I stated in the first slide. So, and this was proved first by Stanley, Richard Stanley, in the year 1980. Okay, so let me just go to the. Okay, this is the three-line proof. Okay, so first you take your polytope. By toric geometry, to this polytope you can associate what is called a fan. So basically what you do is that you look at the faces of your polytope. To each face is associated a direction which is orthogonal to this face. So in this case, for example, we start here. There is a direction. This direction is orthogonal to this face. Then for this face, you have another direction. For this face, you have another direction. And then if you take now vertices, you see that this vertex, in a sense, there is a cone of normal vectors associated to this, which is everything which lies between these two directions, which were normal to these adjacent edges. So what I have done is that I have transformed this polytope into a collection of cones with nicely arranged. So I have one d-dimensional cone for any vertex. For any edge, I have one d minus one dimensional cone, and so on. And these cones are nicely arranged in the sense that if you take the intersection of two of these cones, it will be a common face of both. Okay, so now using this fan, I can construct a toric variety. Okay, so I don't tell you how you construct, but there is a complex algebraic variety. It's actually projective variety. You can associate to X. And it turns out that the edge sequence that I gave you are counting exactly the dimension of H2, the 2i part of the cohomology. The cohomology of toric variety, this toric variety is simple. It is only non-vanishing in even degrees, and if you count the dimension of the even degree part, it gives you exactly the sequence Hi. And if you take, so as I said, this toric variety is projective, so it lives inside a projective space, naturally. And to that projective embedding is associated an element L. Okay, this element is defined by the polytope. This is a hyperplane section. If you take the quotient of the cohomology of X by the image of L by multiplication, you get the finite dimensional graded algebra. And the sequence GI counts the dimension of this. So basically, this is the proof of all the characterization that all the statements of the previous section. This is a beautiful proof by Stanley. So why I talked about this? Because so let's look at what is exactly happening here. Maybe we can get rid of the toric variety and just work with this one, which is in a sense the building block of the theory of tropical varieties. Okay. So let's look at the fan associated to this polytope. This is the drawing I did. If you do it for the cube, you get a three-dimensional fan. It's a collection of cones which are glued together. And it turns out that actually the cohomology group of X admits a representation in terms of this fan. The idea is that inside the toric variety, to each ray of as this fan is associated a divisor which lives in the boundary of the toric variety. The toric variety has a big torus, and it is compactified by adding other tori on the boundary. To each ray is associated a divisor which lives inside that boundary. And the cohomology of to each of these divisors associated an element of H2. Okay? And basically, these divisors generate the full cohomology. So the cohomology of X, it is concentrated in even degrees. For each ray, you get a generator. So now you take the polynomial ring generated by these variables, and the type of relations which give you first of all, these variables generate the full cohomology, so there should be some relations between them. And these relations are very simple to describe. So the idea is that the only way you can have intersections between the divisors which live on the boundary of the toric variety is that the corresponding rays should form a cone. So if you don't have, if the corresponding rays do not form a cone, then the intersection of those boundary divisors should be empty. So the product in the cohomology should be 0. That's why there is a relation given for any collection rho 1, rho k of rays which do not form a cone in sigma. This is the ideal I. And the ideal J is generated by the divisors of meromorphic functions on the toric variety given by monomials. And so this is algebraic way of defining this. But actually, there is a very nice way of defining this relation using linear forms on the Q points of the ambient vector space where the polytope, actually where the fan lives. So for any linear function from QD to Q, you get a relation which tells you that the sum of phi evaluated at the generating vector of this ray. This is the element. This is an element of Z power D, which gives you the direction of the ray. For any linear function, you get one relation between the variables, and these two types of relation describe exactly the cohomology. It turns out that So if you start with any fan, which is not necessarily a fan like this associated to a polytope, you can define the same algebra. So you look at the fan; it's a collection of cones, nicely arranged. And then you can define the polynomial ring generated by variables associated to the rays with these two types of relations. Okay, combinatorial Hodge theory is about description of fans for which you can develop a Hodge theory. Okay, so it's a generalization. So the connection between toric varieties is that if you take a fan associated to a polytope, if you define this algebra turns out to be the cohomology of the corresponding toric variety, so you have all the nice properties of the cohomology of a smooth projective varieties. But you don't need to have. Okay, so let's give a name to this ring. I will call it the Chow ring of sigma because it is the Chow ring. If you look at it in the algebraic sense, it is really the Chow ring of the toric variety. So it gives you its cycles modulo rational equivalence. And this cohomology ring, if you look at if you take a fan which is not complete, which is not associated to a polytope, the cohomology of the corresponding toric variety, you can define that toric variety. The cohomology is complicated, but the Chow ring somehow is simple. It has a certain number of generators and relations. Okay, so if you look at so it's the talk is about tropical geometry. So I would like to define a class of fans which admit a nice theory of a nice Hodge theory. So let's look at what is the property of a fan associated to a polytope. And this is the property that I will use to define more general tropical varieties. So if you look at, for example, in this picture, if you look at this fan associated, okay, so, sorry, there was no. If you look at this fan, first of all, I have any full dimensional cone. If you take any full dimensional cone, I take a face of codimension 1. There is a unique cone which is different from this, which is full dimensional, which shares this, which intersected this cone in this facet. Okay, and the second thing that I observe is that if I take the primitive vector, if I take the generating vector of this ray, if I take this is my tau of dimension d minus 1, if I take this is d-dimensional, this is d-dimensional. These are the two cones which share this d minus 1 dimensional cone. If I take the sum of the generating vector of this ray and this ray, it will be parallel to this phase tau. Okay, so this is something you can check. This is part of the fact that this is a fan associated to a polytope. Okay, so let me define you the building blocks of tropical geometry. So this is the notion of a tropical fan. I would like to get rid of the fact that any d minus 1 dimensional cone is shared by exactly two d-dimensional cones. I wouldn't respect this, but I would like to keep the second property that if I take the sum the rays which are associated to d-dimensional cones which contain one given d-minus one-dimensional cone. These rays, the sum of these rays, the generating vectors of these rays will be parallel to my d-minus one-dimensional cone. So the formal definition, which is the most important maybe definition in this talk, is the following: that if you take, so let's take sigma to be a fan of pure dimension d. I suppose that it is unimodular. This unimodularity is the reflection of the fact, the smoothness that I defined here. So what is the definition of unimodularity? It means that if you take any d-dimensional cone, if you look at any d-dimensional cone, if you take any d-dimensional cone, you have exactly d rays, which define that d-dimensional cones. And if you take the primitive vector of those rays, those primitive vectors generate the lattice, the integer points of the vector space defined by this cone. Okay? So basically, any integer vector that you see inside this cone is an integer linear combination of these vectors, which generate the cone. That is the meaning of unimodularity. Yes?
You'll always be looking like fans embedded in some ambient.
The fans are embedded, exactly. So you will see it's very important because you want to talk about, even for the charring, I needed to have linear functions which were defined in the ambient space. So I denote, this is the notation, I denote sigma k is the k-dimensional cones. I suppose that my fan is pure dimensional. It means that if I take the maximal dimensional cones, they all have dimension d. I don't want to have something like this, because this is that dimension 2. This is a maximal dimension cone of dimension 1. It's not allowed. So all the maximal dimension cones have dimension d. So I endow this sigma by a tropical orientation, which is an association of weights to top dimensional cones. These weights are positive integers. If you don't like to work with weights, you can suppose that all of them are equal to 1. But in a minute, I would like to define I would like to show you a lot of tropical fans coming from geometry or constructed by using some operations on tropical fans. So as soon as you start working with tropical fans, you should get rid of having weights equal to 1. That's why I put weights having positive integer values. This is called a tropical orientation. And this balancing condition is exactly what I told you, that if you take a d-minus one-dimensional cone, you look at all the d-dimensional cones which contain that tau, okay, that this is tau, then there is a vector n sigma tau which generate the unique ray of sigma which is not in tau. Then you take the weighted sum of these generators of the rays of sigma minus tau, with weights given by omega by the weight of that cone. This should be parallel to tau. This will play, from the cohomological point of view, this will play the role of an orientation, because I will use this to define fundamental class associated to tropical varieties. So I can talk about Poincare duality. Without this condition, we cannot talk about any of the results that I mentioned. Okay, so the pair sigma omega is called a tropical fan. So let me tell you how you can construct these tropical fans. Okay, so the first example is a tropical line. What is a tropical line? So it's a fan of dimension 1 in Rn. So you look at Rn. You take all the rays associated to the coordinates. So this is R plus E1, R plus E2, R plus En. The primitive vectors are E1, E2, En. If you do the sum, you get what you get. You get E1 plus E2 plus E3 up to En. So what you do is that you add an extra ray now, which is R plus, generated by, you take the ray generated by minus E1 minus E2 minus En. So now this is a fan of dimension 1. It has exactly n plus 1 rays. And if you look at around a unique codimension 1 face of this fan, which is the origin, the sum of these, the weights are equal to 1. All the weights are equal to 1. then the weighted sum of these vectors is 0, okay, which is parallel to this vertex. This vertex, the tangent space to this vertex is 0, so this is the balancing condition. But what you can do is that you can take this line, and then you can just put all the weights equal to 2. You get another example of a tropical fan. Okay, so we can put any weight as soon as all the weights are equal to each other. So you cannot change. The second source of tropical fans comes from tropicalizations of algebraic varieties. Okay, so what is the tropicalization of algebraic varieties? So you take X, a subvariety of C star power n. So it is given by a finite system of polynomial equations. In each polynomial is a Laurent polynomial in n variables. And what you do is that, so basically, classically, you are interested in finding complex valued solutions to that system of polynomial equations. But now what you do is that you enlarge your field K by adding a parameter T to C. You look at all the let's say, Laurent power series inside in parameter T, and then you look at the solutions of that system of polynomial equations inside this bigger field. But you are not interested in having the solutions. You are interested just to see what are the exponents, the minimal exponent of the parameter T in each coordinate. So that is described in terms of evaluation. So you have evaluation, T-adic valuation defined on the field of Laurent power series in T. And then you tropicalize each point Z, which is a solution of that system of polynomial equation. You just remember the T-adic valuation of the coordinate. This gives you an element of Rn. If you are working just with Laurent power series, you just get integer points. So then you say, okay, I would like also to look at the algebraic closure of the Laurent power series. So I allow to take Laurent power series in T power some rational numbers, some T power n divided by 10, n divided by 100. And then you get more and more points in Rn. I'm sorry. So these are the tropicalizations. So this is the ring of, this is the field of Puisa series. So these are Laurent power series in any rational power of T. The tropicalization gives you a lot of rational points in Rn, and the closure of this gives you a topological subspace of Rn, and it turns out that this is support of a tropical fan. So the weights are described using tropical geometry. You put any fan structure on this tropicalization, it gives you a compactification of partial compactification of C star n, and you take the closure of X inside that partial compactification. Okay, so it gives an actual compactification of X, and then you calculate the multiplicity of intersection with some specific strata which appears in the boundary of the toric variety. It gives you the weight. So the multiplicity of intersection with the some boundary strata inside the toric variety gives you the weights, and it will be a tropical fan. And it turns out that there is a third source of source of examples. This comes from metroids. So I think I already spent a lot of time to. So I will come back to the metroids a little bit later. Okay, so now I would like to tell you how you can construct. So I gave you basically two examples: tropical line, which was this line, which is in Rn. And then I told you also that you have a source of example coming from algebraic geometry. So let's forget about algebraic geometry. I would like to construct a lot of tropical fans. Okay, usually what you do in algebraic geometry is you have some operations. So let's do the same type of operations here. So you start with a collection of tropical fans that you have already constructed, and then you can take the product. So you take two tropical fans, sigma 1, sigma 2. You take the product. It means that the cones you see are a cone inside sigma 1 times a cone inside sigma 2. The full dimensional cones are exactly a full dimensional cone in sigma 1 times a full dimensional cone in sigma 2. You have weights omega 1 here, omega 2 here. You take the product. It turns out that this will be, again, the tropical fan. It means that the category of tropical fan is closed on the product. And I just explain you how to define this. The second property is barycentric subdivision. You start with a tropical fan like this, and then you just subdivide. So you have these generating vectors. You look at the direction, which is given by the sum of these generating vectors of the ray. It gives you a new ray, and you subdivide the fan. The fan, you subdivide the cone inside the fan. This is called the barycentric subdivision. it is related to, from the toric geometric point of view, it corresponds to doing a blow-up, okay? And you subdivide, and then you don't change the weights. So somehow you look at the induced weight on this subdivision. This gives you another source of examples. The third one is the most interesting one because so far the product was just the support of the fan were the products of the supports, and the bicentric subdivision doesn't change the support. So the third property is something specific to tropical geometry. It's called tropical modification. It's important because it allows you to change the ambient space where the fan lives. So this is called the tropical modification. It is obtained by doing a little bit of complex geometry somehow in the tropical setting. So I define what I'm doing here. It's called tropical modification. I take a function f, which is defined on sigma, which is conwise, it is continuous, it is conwise linear. So on each of my cones, I have given myself a linear function, the restriction of a linear function, and they are compatible on the intersections, and globally, so I get a continuous function. I suppose that these linear functions are integral. So I view these functions as in toric geometry as meromorphic functions defined on my fan sigma. So I would like to define an order of vanishing associated to each of these meromorphic functions. So usually tropical geometry, order of vanishing is obtained by doing the sum of the slopes. So I can't tell you exactly what is the definition. So if I wanted to explain you what is the source of the geometric source of this, it would take a little bit of time. But the definition is very simple. So what you do is the following. You want to define the order of vanishing of f along a codimension 1 cone. Divisors correspond to, the order of vanishing is usually along a codimension 1 hypersurface or divisor inside. So I do the same thing. So I look at sigma. Sigma has dimension d. I take a d minus 1 dimensional cone. I look at the order of vanishing of f. I would like to define this. What I do is the following. I look at, basically I am calculating the sum of the slopes. From the distribution point of view, I'm derivating my function. And then I get the sum of slopes of my derivation along these codimension 1 faces. I'm really doing distribution theory, but it's very explicit from the polyhedral geometric point of view. So I look at f for any, so I have my cone tau here. I have, let's say I have two-dimensional, d-dimensional cones. This is my cone tau. So if I take a sigma here, I have a unique ray, which is in sigma, but which is not in tau, and I have the corresponding generator, n sigma tau. So what I do is that I calculate, I evaluate my function f at the generator of this new ray, but I take the sum of these values, but weighted sum. With weights are given by the tropical orientation. Each sigma comes with a weight. I get minus the weighted sum of the values of f at these generators. And then I add a correction term, which is given by taking the value of f, add the weighted sum of n sigma tau's. So the weighted sum of n sigma tau is parallel to tau. So I know that my function f is linear on tau. It's given by a linear function, which is defined on tau. I can evaluate f at this vector. So this is called the order of vanishing. Then I define order of vanishing along codimensional 1 faces. I can tell you what are the holomorphic functions. Holomorphic functions are conwise linear functions, which give you always non-negative orders of vanishing. So now the idea is that I would like to define a new tropical fan. What I do is that I call this the divisor of f. The divisor of f is basically, I define order of vanishings, and the divisor of f is a sub-fan of sigma defined by all the tau's such that order of vanishing of f at tau is non-zero. It's the support of the function order of vanishing. Okay? So I have defined a sub-fan of sigma plus a weight function on this. And it turns out that this will be a tropical fan theorem. So this is one of the basic results in tropical geometry, that this is, again, a tropical fan, provided that these order of vanishings are non-negative. Okay? Yes? So in the toric case, the codimension 1 face corresponds to a curve. And these numbers correspond exactly to you take the restriction of your function to that curve. And to any d-dimensional cone, you get a point, and you are calculating the order of vanishing of the restriction of f to that curve. So by, you know that the sum of the order of vanishing is 0. Sorry? So what you get, so what, if you, okay, so if your question, of course you will construct a new toric variety, but the compactification of, okay, so from the toric geometric point of view, I will change the fan, so I will tell you how you change the fan. So you will construct a new toric variety. But the compactification of X does not change. Okay, so what you do is that you take, I define this order of vanishing, I get a divisor F, which is a subfan of sigma of dimension d minus 1 plus this order of vanishing as a function. So now I take the graph of this function F. The graph of function F lives inside sigma times R. So if let's see what is the shape of this graph. The shape of this graph is as follows. So let's say we are in dimension 1. I take the order of vanishing. So I have a function. So my tropical fan was the tropical line inside R2. I take a function which has a slope minus 1 here, slope 0, it's constant here. So the order of vanishing at this point is 0. So now I take the graph of this function. Okay. So what I see is that if I look at this is again a fan. But if I do the sum of the primitive vectors of this rays, it's not any more balanced. But there is a way to turn it, to make it balanced, is by adding all the cones, tau times R plus. So I basically add this new cone, and I put the order of vanishing of f at tau. So if this is my tau, I add this, and this becomes again a tropical fan. Okay. So what I have done is that now I have a fan which is embedded not inside Rn, it's embedded inside Rn plus 1, and it has a new cones given by the divisor of this function f. And theorem, if I add all these cones with this order of vanishings on these new cones, top dimensional cones, here and the omega here, this will be again a tropical fan. You see it in dimension 1, but this is a general statement. So the divisor of fan is obtained by defining order of vanishings, and then you take the support. It means that you look at all the codimension 1 cones, which give you where you have an order of vanishing which is non-zero. Otherwise, the other ones, they are not in the support, you forget them. And then you look at the subfan given by these cones and or their faces. And you put these numbers as the weight of that fan. Okay? This is a tropical fan. And the tropical modification is obtained by by taking those cones and multiplying them by R plus inside Rn plus 1, inside a bigger ambient space. Okay, so why this is interesting? Because to each of these tropical fans, I can associate a Chow ring. So if I have a fan, we saw that I can define that Chow ring, which was generated by the rays, variables associated to the rays with two types of relations, I and J. So I can define to any fan like this that I obtain, I can associate a Chow ring. Okay, so this is maybe the generalization of this picture to this Polytop picture. So you start from from the tropical line. Okay, so let's say you can start from this example. This example is you have just a point. You have two directions, and you can put any numbers, any positive integer numbers. And then you perform a sequence of these operations, taking product, subdivision, and tropical modifications. Tropical modification so the divisor should be also part of you suppose that the divisor is already constructed. So you do a tropical modification, assuming that the divisor is one of the tropical fans you have constructed. Theorem, this is a theorem. Basically, all the Chow rings that you get verify the Keller package. They verify the Chow ring verify the Poincare duality, Hard-Lefschetz theorem, and Hodge-Riemann relation. So why this theorem is interesting? First of all, it gives you a large collection of tropical fans, which verify all the basic theorems of Hodge theory. But it allows you also to prove a an important result by, to reprove, given basically a simple proof of a recent result by Adiprazito, Hu, and Katz on, in Hodge theory for metroids. Basically, to any metroid, I didn't define a metroid. To any metroid, you can associate one of these tropical fans, and it turns out that that tropical fan can be constructed by a result of Chris Shaw by doing this sequence of operations from the line. So basically, you get a new proof of a breakthrough by Adiprazito, Hu, and Katz in combinatorics, because they could use, along the lines of the work of Stanley, they could use this Hodge theory for metroids to prove a lot of conjectures in the theory of metroids. So this has played an important role in the development of combinatorics in the last 10 years. So now this is the new proof, and the proof is actually, you prove that any of the operations that I defined, verify, preserve all these properties. The product, you use Kunet theorem. The subdivision, you use projective bundle theorem, which allows you to describe the charring in terms of the charring of the original fan and the cone that you subdivided. And for tropical modification, it took me more time to describe what is the tropical modification. But in terms of this theorem is the easiest, so you have to prove something, but the easiest part in the sense that the tropical modification, what we prove that the tropical modification does not change the charring. So if you had the charring, which was verifying tropical, the Poincaré duality or hard-left and Hodge Riemann, after the tropical modification, the corresponding charring verifies. Okay, so let's for the rest of the talk assume that call any of these fans that was obtained from the tropical line by a sequence of product, subdivision, and tropical modification along divisors which were already defined. Let's call these tropical fans scalar tropical fans because they verify all the category of scalar tropical fan is a little bit large. I mean, it's larger, strictly larger, but this is basically, it's a little bit more technical to define what is a tropical fan, scalar tropical fan. But this is basically, you saw that you can construct a huge collection of scalar tropical fans. Now I would like to do a little bit of scalar geometry with these ones. And I don't know how much time I have because I took, 11 minutes? Okay.
11
Okay. So I think the good thing is that my talk, it's relaxed. So I planned a lot of different topics, so I can stop at any moment. It's somehow the sections are independent. So let me just. So is there any question before going to the global geometry? I would like now to tell you how you can define more general tropical varieties. So these tropical fans will play the role of Cn in the theory of complex manifolds. So I would like now to construct global tropical varieties using these tropical fans, these scalar tropical fans. These are somehow the smooth charts. I will take my charts inside these tropical fans and the compactification. Is there any question?
So what's this function? There are many of them, or?
I didn't. Okay, so yes. Okay, so yeah, I didn't tell you. So there is. Okay, so there was something that I put it on the carpet. Is that to this polytope we saw that there is an element of H11, H2 of the toric variety, an element of A1 which was associated to the polytope. That one corresponds to a convex function defined on the fan, and this notion of convexity, it makes sense for any general fan. So a function h, maybe I keep it. So so the function h is called convex if it is conwise linear, and if you look at it, around each cone inside your fan, you can modify your function with a global linear function by removing a global linear function, so that to make it 0 on that cone and strictly positive on the complement of any cone which contains this as a face. So you make it, so if this is your picture, you have a function which is conwise linear. You can modify this with a linear function phi, so that it becomes 0 on this, and it becomes a strictly positive on this cone. So it's a notion of convexity for more general fans. Sorry? If you take the projection by killing this toe, you get a fan, and you get a strictly positive function, linear and positive function, exactly. So there's a way to go to the quotient of the cones around this toe and get a positive function. This reflects the fact that the fan in this picture, in the toric picture, was coming from a polytope. This is the notion of convexity, which makes sense also for more general fans. Okay, so first of all, I would like to tell you, so I want to define tropical varieties by gluing charts. So what I do is that I take one of the fans, one of these tropical fans that you saw, I compactify it, because, so what is the compactification? The compactification is easy. So you take any cone inside sigma. This cone, if it has dimension k, it is generated by k rays, so it looks like r plus power k. So you allow the coordinates to become infinity. Okay? So if you have this picture, even in this case, you get something interesting. So this, you take this cone and you just add a copy of this ray at infinity. So you add this point infinity on each ray. And then you transform all these cones into cubes. So the picture even in the complete case, in the case where you started with the polytope, is something interesting. So now I have compact objects. So this is an example of this type of compactification. So what I do is that I define a general tropical variety by an atlas of charts. So I take a topological space and I endow it with an atlas of charts. UI, I suppose that there is an atlas of charts UI phi I, such that phi I UI are open sets inside X, and phi I identifies UI with an open subset of one of these compactifications of some tropical fan. Okay, so this is the usual way of defining manifolds, but you have to tell what are the transitions, maps between the charts. So we are in the polyhedral setting, so if there is an intersection between UI, uj inside X, then you can go, by using phi j, you can go to sigma j bar, and by using phi I, you can go to sigma I bar. So then there is a transition map between the image of phi j on UI intersection uj to the image of phi j. And you ask that this map is induced by a global linear function, which affine function, which has a linear part defined by integer coefficients. So it should be integer. So it's about integer linear maps, integral linear maps. Okay, so maybe two examples. So if you have a manifold, integral affine manifold, so you take any real manifold, and you suppose that you have an atlas of chart, the transition maps are defined by affine function with integer slope, with integer coefficients. This is an example of a tropical variety. I have to suppose that the weights are on sigma I and sigma j are consistent, so you can make sense of this, so that I get also a weight function and orientation on my X. So here, if I have an integer affine manifold, we are locally like in this case, the weights are all equal to 1. Okay, so I don't need I put weights equal to 1. So integral affine manifolds are examples of, without singularities. Okay, so these are examples of these tropical varieties. Metric graphs are examples of tropical varieties. So a metric graph is a graph. So you start with a graph. And what you do is that you take a function, length function L, on the edges of the graph. And you replace each edge with an interval of that given length. Okay? So this gives a topological space. I have a topological space where I can, along this edge, I have length, for example, 3. Or along this edge, I have length pi, number pi. And I have to tell you what is how you put a chart on this. What you do is that you take any vertex. You can define a star along this vertex. You take an open subset, which is given by these branches, and you identify these open sets by an open subset of this tropical line with weight 1. Inside, if you have here you have 3 edges, you identified with the tropical line inside R2. You have exactly 3 branches. And you can check that the transition between the charts are again given by affine function. So any metric graph is an example of a tropical variety. No. Okay, so now I would like to define the cohomology of these tropical varieties. So basically, the idea is that in Hodge theory, you know that HPQ, that the groups HPQ that I defined, admits a description in terms of degree P holomorphic forms. So HPQ is isomorphic to HQ of the projective complex projective manifold with coefficients inside omega p. So the idea, which is due to Ittenberg, Kazarkov, Mikhail-Kazarkov, is to define the analog of the sheaf of degree P holomorphic forms on a tropical variety, and then calculate the cohomology HPQ by taking the Q cohomology of X with values inside this coefficient group. So in order to define FP, I have to tell you what are the multi-vectors, holomorphic multivectors, tangent to my tropical variety at the point X. And then I take the dual of this. Okay, so this is the dual of this sheaf of tropical P holomorphic form, degree P holomorphic forms. So I define it at each point X as follows. I take the Q vector space generated by P multivector, and this multivector V1, the elements of in this which appear here, V1, V2, Vp, are tangent to X at the point X. So they correspond to tangent vectors to X at the point X. But in addition to this, there is an extra condition, is that if I take the weighted sum of these vectors with very small coefficient, the germ that I get is entirely inside X here. For example, in this picture, I would like to calculate the two multivector around this. I can take 2 vectors like this, which live together inside this 2-dimensional cone. If I take the positive sum of these vectors, I will be entirely inside here. I can take also 2 vectors which are tangent to this cone. Then the positive combination of these will be inside here. But I'm not allowed a priori to take a vector here and a vector here. Because if I take the positive combination of this, I might go outside the support. Okay? But it might be the case that I can find this multivector as a linear combination of the ones that I am allowed to take. Okay? So then this defines this FP, and the dual of this will be my sheaf of degree P holomorphic form, and then I define the HPQ of X with values in HQ of X with the coefficient inside this FP, and I call this HPQ of X. The idea is that this HPQ should play the role of the HPQ in the Hodge decomposition, and this is exactly what I'm going to tell you. So let me give you an example. So if I define what is a metric graph. So if you take a compact metric graph and you put this atlas of charts that I described, then you get this very nice computation. It's an easy computation. So if you calculate H00, you get Q. If you calculate H10, H01, you get Q power G. G is the first Petit number of the graph. Okay? So it's the number of independent cycles and the number of holes that you see here. So in this example, the number of holes is 2. H10 is isomorphic to Q power G, H01 is isomorphic to Q power G, and H11 is Q. So if you replace Q by C, what you see is exactly a shadow of a Riemann surface of genus G. Okay? So in this sense, this metric graph with this atlas of charts that I define is the first example of Kähler tropical varieties of dimension 1. These are basically Kähler tropical varieties of dimension 1. So the second result is a computation of this HPQ for a compactification, one of these canonical compactification, which makes the connection to the charring. At the very beginning, I told you that the charring of sigma was the cohomology ring of the corresponding toric variety. If you are working with Fan, which is not complete, which doesn't cover the full space, you cannot hope, there's no hope you can describe the charring as the cohomology ring of some complex algebraic variety. But you can basically, this result tells you that you can describe the charring of any fan as some part, as the Hodge part of the cohomology of sigma bar. So if you calculate HPQ of sigma bar, in BI degree P equal to Q gives you AP. You have vanishing, and if your sigma is scalar, then basically the charring is entirely described. So it's not HPQ here, it's H dot dot. It means that all the HPQs for P different Q are 0 if K sigma is scalar. All the HPQs are 0. The only ones which are non-zero are the diagonal ones, and the diagonal ones is exactly the charring. So I finished here. So okay, I told you that the weight allows you to define the fundamental class. The idea is that if you have a tropical variety, which I just defined, you can define the fundamental class, and the fundamental class lives inside HDD. So this is the homology of X with coefficients inside the FD homological, and you can define this is defined by cycle. This cycle has a very explicit description in terms of a volume form that you can put on any top-dimensional simplex inside X. And using the balancing condition, you can check that this is a cycle. And using this one, you can make sense of the Poincaré duality, because you take the cup product, these are cohomology groups, you can take the cup product and then intersect with the fundamental class. And the theorem proved by Gell, Shaw, and Smaka. So this was proved for the case where you had very tropical varieties modeled by metroids, but actually the proof is a local global property. So if you have local duality, you glued by charts, then you get a global duality property. So basically, if you are working with X and the defining charts of this X are Kähler tropical fans, then you have Poincaré duality. Okay, so maybe I can tell you, so maybe I just stated the main theorem of Hodge theory, and I think then I just stop unless you have questions about. So let me define you, give you the definition of a Kähler tropical variety. So as in the complex geometry, how do you define Kähler complex manifolds? You say that, okay, so these are defined by taking an atlas of charts. Transition math should be holomorphic, but in addition to this, you ask the existence of a Kähler form. So we take the same definition. So X is Kähler if the tropical fans which define X are all Kähler, or the sigma I which were used to pick the charts, they are Kähler. And in addition, there is a global Kähler class, L inside H11X. So it means that basically, for example, if X is defined inside TPN, then you have a global, it's a projective case. Then you have a class L, which is the class of a hyperplane section inside the projective tropical variety, and it gives you an element. But this is more general. Basically, you want to have an L such that if you take the restriction of L on all these sigma I bars, you get a Kähler, an element of H11 of that compactification. But the element of H11 of that compactification is an element of A1. So I told you what are the elements of A1, which corresponds to Kähler forms. Okay, and the main theorem is that, so basically the analog of all the statements about the cohomology of complex varieties, you have it here. So if you have X, which is the Kähler tropical variety, L, a global Kähler class inside H11, then you have, first of all, you have the Hodge symmetry. HPQ is isomorphic to HQP. There's no complex conjugation. It's really symmetric. You have Hard-Lefschetz theorem with respect to this global L. So if you take the product enough time of enough right power of L, it gives you an isomorphism between HPQ and HD minus QD minus P. And then you have Hodge-Riemann bilinear relations, which tells you that they induce pairing on primitives. You have to define primitive parts. This is defined. Okay, I just tell you, I finished by I told you that tropical varieties of dimension 1 corresponds to Riemann surfaces. In dimension 2, you get the Hodge index theorem out of this for tropical surfaces. So if you look at the H11 of a tropical surface, which is Kähler, then you can describe the index of the intersection product. And then, so usually in complex geometry, you have index 1 positive eigenvalue and this many H11 minus 1 negative. But in this case, you get something different, which is n plus the second Betti number of the tropical variety. And this is the number of positive eigenvalues, and the rest is Okay, thank you very much. I think I went half of my time.